Hello, we're Group 16 and this is Project 1. Our project is automatic manual transmission. My name is Daniela Chavez and
I'm Daniela Oliva.
Okay, so now Daniel is gonna explain you how a gearbox works.
The manual transmission gearbox has been around for a very long time. It's a very simple design and it works basically by getting the rotational motion from the engine, transmitting it through the lay shaft, and then to the main shaft through the gears on the main shaft. The gears on the main shaft are mounted over bearings so they do not transmit power directly. The way that power is transmitted out to the output shaft is by using the dog clutches, which are highlighted in purple. When the clutch pedal is pressed inside of the car, the power from the engine is disconnected to allow the dog clutches to slide onto the main gears on the main shaft. The gears on the main shaft have teeth which match with the teeth on the dog clutch. The dog clutch gears are moved using a selector mechanism, which is shown over there. After the clutch pedal is released, the dog clutch is fixed onto the main shaft, so then power is being able to is able to be transmitted through the input shaft to the lay shaft to the main gears, and then out to the output shaft, which is then transmitted to the differential and out to the wheels again. Daniela will now talk about the theory behind gearbox design.
So the gearbox theory. Basically, we have two concepts that we really need to know. The first one is the gear ratio. The gear ratio is going to relate the input speed and the output speed of the input shaft that you can see here and the output shaft. And here is the gearbox. Okay. Also, it's going to relate the angular speeds of both shafts, the input and the output. The next concept that we need to know is torque and also how it is related to efficiency. Here you can see that torque is applied at the input shaft and torque is generated at the output shaft. Also, remember that since the gearbox is not holding in place, the torque at the input and the torque at the output shafts are going to generate another torque in the gearbox. So a clamp is needed to hold it fixed. This torque that is generated on the gearbox is torque 3. The power transmitted by the shaft is related geometrically by multiplying by 2 pi, and also is related to the torque and is related to the speed, and it's divided by 60. So for an ideal gearbox, you have that the input power is going to be equal to the output power. You can see here the mathematical relationship, and here we are going to end up with these ratios. From this, we are going to find T2 over T1 equals N1 over N2, which takes us back to the gear ratio. This way, we're proving that the gear ratio is related to the torque, input on the shaft, and the speed of the gears. Finally, we have efficiency. Efficiency is going to be related to the power output and the power input. As you can see, now the torque and the speed are related, and here we have our final solution, which is N2 times T2 and N1 over N1 times T1. It's important to remember that the torque, the input torque and the output torque are different. So, well, I already said that a gearbox has to be clamped in order to stop the case or body rotating. Hence, holding torque 3 is applied to the body. And also, it's important to remember that the total torque should add up to 0. So, T1 plus T2 plus T3 equals 0. All of this is going to be true when you have an ideal gearbox. Well, I already finished with the gearbox theory, so now Danny is going to talk to you about the proposed idea for project.
Right. So for our proposed idea, we selected two models to compare side by side. The Ford Focus Titanium Hatch model and the Ford Focus ST model. The main difference between these two models is that the Ford Focus ST carries a 6-speed transmission, while the Ford Focus Titanium Hatch only has a 5-speed transmission. We believe that the 5-speed transmission is a very inefficient model, as shown by the gear ratios here. As you can see, the last gear on the 5-speed transmission has a 0.81 to 1 ratio. This means that for every 0.81 turn of the input shaft, you get 1 full rotation of the output shaft. This may seem good because the input shaft is doing less work than the output shaft. However, when you're driving the car in real terms, if you only have a 0.81 to 1 ratio for the 5th gear, this means that on the highway, going about 60 to 70 miles per hour, you're going to have the engine rotating at about 3,000 RPMs. This seems a little bit inefficient, especially for fuel economy, because if you're driving over long periods of time, it puts a lot of strain on the engine and wastes a lot of gas. You can solve this problem by adding an extra gear, which may have a 0.6 to 1 ratio that the driver can shift into when cruising at highway speeds. This will allow the car to waste less fuel and also give the customer a nice smoother ride at a lower RPM, and this may be beneficial to him and give him more satisfaction driving over long periods of time. As you can see, we see that the Ford Focus Titanium Hatch and the Ford Focus ST model only differ between about $50 of price. This shows us that adding an extra gear, such as the 6-speed manual transmission for the Ford Focus ST, will not increase the price significantly, so the customer will not be affected directly. This also shows us that manufacturing costs for the Ford Focus ST do not differ greatly from lower end models. So because of this reason, all Ford Focus models should carry the 6-speed transmission because of the fact that it will not increase the price significantly. It will overall increase the customer satisfaction and increase fuel economy.
So as a conclusion, in this project, we learned about gearbox design, how the gear ratio is related to the fuel consumption of the engine of the car. And we also concluded that if we reduce the gear ratio, we're going to have a less fuel consumption from the engine, and our customer is going to be satisfied. As a final point, we added a video of how the gearbox works in real time. We're going to show it, and thanks for your time.
This section examines gearbox operation. In a rear-wheel drive manual transmission, the splines on the input shaft engage with the splines of the clutch-driven plate. With engine rotation and the clutch engaged, the input shaft transfers its motion through the countershaft to rotate the gears on the main shaft. In this neutral condition, the engagement sleeves and hubs splined to the output shaft are stationary. No drive is transmitted to the output. Depressing the clutch pedal removes the engine load from the input. This allows an engagement sleeve to be moved into engagement with the external teeth on the gear selected. This locks the gear to the main shaft. When the clutch is released, the drive is transmitted to the input gears along the countershaft to the gear selected. Since this gear is now locked to the main shaft rotates and transfers the drive to the final drive unit. The speed ratio and the torque transferred depend on which gear is selected. In this 4-speed transmission, first gear, the smallest on the countershaft, meshes with the largest gear on the main shaft to give first gear. This is the lowest forward ratio. The greatest number of turns of the input are required to achieve 1 turn of the output. This also gives the greatest torque multiplication. In second gear, power flow is through the next adjacent gear. The difference in speed between input and output shafts is reduced. Fewer turns of the input are required to give 1 turn of the output, but there is less torque multiplication. When the engagement sleeve for third gear moves into place, drive is transmitted through the meshing gears at an even higher ratio. In fourth gear, the input and output shafts are locked together. This provides a direct drive with a 1-to-1 ratio, with no reduction through the countershaft gears. The input and output shafts turn at the same speed, and therefore there is no torque multiplication. The countershaft gears and their corresponding gears on the main shaft continue to rotate, as the countershaft is constantly in mesh with the input gear, but they do not transmit any drive. With the vehicle in motion, these gears will be turning at different speeds in relation to the main shaft and to the engagement sleeve, which is locked to the main shaft by the spline. When changing gear, their speeds must be synchronized so that the engagement sleeve can move smoothly into engagement.